Hey everyone, this is Dr. Walker. This is video 16C. It's called Kinematics in 2 and 3 dimensions. The great thing about this video is that it's very similar to what we've just done, one-dimensional kinematics. The only difference is we have to use full vector notation. Let's start with position and displacement in 2 and 3 dimensions. If we look at this picture, it shows the x and y direction, so we're in a two-dimensional plane here. And we have the path of a particle shown with this dashed line here. So the particle is moving along this line. Let's say if at one time it's at this position A, then it goes this way, and then at another time it's at this position B. So how do we describe the position at A, for example? Well, the position is described with a vector. In this case, because this is the initial time, we can call it r initial. But in general, the position vector is just r, so how do we write this? Well, this vector has an x component and it has a y component. It could even have a z component, just not shown here. So in 3 dimensions, we would say x I hat plus y j hat plus z k hat. Note that when we were in 1 dimension, we had maybe a number line here, and we said, hey, this is the origin, and maybe our position at some time later was here at 5 meters. And so we could just say it was 5 meters to the right, or just positive 5, and that positive number implied the direction. But in this case, when we're in 2 dimensions, we have to specify the position with a vector which has a magnitude and also a direction. What about the displacement vector? We said displacement does not depend on path, and it still doesn't in 2 or 3 dimensions. So if we're going from point A to B, the displacement only depends on the endpoints. And before we said delta x, for instance, was xf minus xi. It was just a difference in positions. Well, now it's the same thing. The displacement between 2 points is just the subtraction of the 2 position vectors. So delta r is going to be defined as the rf minus ri. We can see in this picture here that we have position vector ri pointing towards A, rf pointing towards B, and delta r, the displacement vector, points from A to B. And this does happen to be the subtraction of rf and ri. And if you don't see that rf is indeed equal to this, what you can do is you can redraw ri as, you can draw negative ri. Remember, a negative vector goes in the opposite direction. So negative ri goes this way. And then you can see that we have rf, and then tip to tail, right, minus ri or plus negative ri. And we started here, we ended here, and that's how we learned to do vector subtraction. So we can see delta r does point in this direction. Let's take a look now at the velocity vector in 2 or 3 dimensions. This picture shows the 2-dimensional path of a particle with the dashed line again. And if we are looking at 2 points, for instance, point A and B, then we know that the displacement is this displacement vector r1. We could draw the displacement vectors r initial and rf if we wanted to. We don't really need to for this because we're looking at velocity, but I'm just summarizing what we just talked about again. So now if we want the average velocity from A to B, well, it's going to be defined just as before, displacement over time. So the average velocity is going to be delta r divided by delta time. So that means that from A to B, the average velocity is going to be in the same direction as the displacement. Again, we don't need these position vectors. I was just showing you to show you where the ri delta Ri was coming from, R1 was coming from. What about instantaneous velocity? Well, let's say we want to find the instantaneous velocity at point A. We know that if we find a limit as the time interval approaches 0 of r over t, then we get derivative of r with respect to t. So this picture is just showing that as the time interval gets smaller, and the delta r is also getting smaller, and we are getting closer and closer to the green line, which points in the direction of the instantaneous velocity at that particular time. Please note that because the velocity is dr over dt, we can also write it in unit vector notation. So another way to write the instantaneous velocity at any time is to say, well, it's going to have an x component in the I direction plus a y component, j direction, plus a z component, k direction. So we can definitely, and will in the examples that follow, write the velocity vector using unit vector notation. Let's take this one step further to acceleration. It's going to be a very similar process. We know that the acceleration is a change in velocity per time. So that is how it is defined, whether you are in 2 or 3 dimensions. If you look at this picture here, which again shows the path of the particle with a dashed line, it shows the instantaneous velocity vi at position A at that certain time initial, and then the instantaneous velocity at time final at point B. You can see that the velocity is changing directions. So there is a change in velocity. We actually will talk about this more when we talk about centripetal acceleration. But for now, just realize that an acceleration is a change in velocity, and delta V points in this direction. If you subtract the vectors, you can do the same thing we just did and do VF, and then you can put VI, negative VI this way, and use a tip to tail method to get the delta V going this way, delta V here, which is the same thing that we get here. And so that means that the average acceleration of the particle as it's moving along this path, average acceleration is going to point in the same direction as the change in velocity. You can imagine what the equation for instantaneous acceleration looks like. I'll go ahead and show it to you. It is the derivative of the velocity as a function of time. And you can also write the acceleration as a vector in unit vector notation. It will have an x component, I hat, plus a y component, j hat, plus a z component, k hat. Let's look at a couple more equations before we are ready for some examples. Let's look at 2 kinematic equations. These are the ones we most commonly use. So first, let's look at the kinematic equation that gives us the velocity. Do you remember Vf equals V initial plus At? That equation? Well, we can write it in vector form now. So V final equals V initial plus At. But if we're going to write it in vector form, we just have to put the vector signs here. We'll do an example where we use this equation in either 2 or 3 dimensions. What we see here is a graphical representation of this equation. It shows us that if we have an initial velocity vector, vi, and then we add an acceleration multiplied by time vector, that the resultant is vf. This graphical representation shows us that vf is typically not in the same direction as vi and with also a different magnitude. So having this acceleration when you have this initial velocity results in your velocity changing. So it's just a different way to look at it. And the position vector can be written as follows. This has broken up the RF and the RI If you want to write it the way that we wrote the kinematic equations in one dimension, it would just be delta R equals v initial t plus 1/2 at squared. And once again, we have a graphical representation of this equation. There are two main ways to use these equations. One is to just make sure to write all of these vectors using unit vector notation. We're going to do this in an example that follow. And then another way to use kinematics in 2 or 3 dimensions is to just to write down the direction separately. So we have a vector equation, but we can write it separately for the x, y, and z direction. Let's take a look at some examples.